These examples will show how to compare two sample proportions. So if you've taken two samples and you want to compare, say you think one sample is doing something better than a different one, and you have proportions to compare, this is the type of test that you would do. So we're going to use subscripts 1 and 2 to make sure that we keep track of what sample 1 and what's from sample 2. Then we need to use something called a pooled proportion, which is a p with a bar over it. And that's going to be the two x's added together divided by the two n's added together. And then q with a bar over it equals 1 minus p with the bar over it. The null hypothesis for these tests will be that p1 equals p2, or you could write them p1 minus p2 equals 0, meaning there's no difference between the two groups. Right, the equations here, we have an equation for z-score, the difference between the two sample proportions, p hat 1 minus p hat 2, minus the difference between the two population proportions, which we're going to say is 0, because the null hypothesis says that p1 and p2 are the same, so there's no difference. So 0 is going to go in for that. On the bottom you have p with a bar, the pooled proportion, pooled sample proportion, and q with a bar divided by n1, and then plus p with a bar, q with a bar divided by n2, and take the square root of all that. So it's kind of a complicated equation for z. We'll do one example using the equation and then see how to use the calculator to do the same thing. We're going to use z again, standard normal distribution. Here's the equation for the confidence interval. Again, it's a fairly complicated equation, lots of stuff in it, but our calculator does a two sample proportion z interval as well as the z-test. So some requirements to watch out for. We need simple random samples for both samples, sample 1 and sample 2. They have to be proportions, x out of n, and we have to check np is greater than 5 and nq is greater than 5 for both samples, so a little bit extra work to make sure that you can do these tests. Alright, three methods. Again, we have p-value method, the critical value method, and the confidence interval method. And we're going to look at all three types for our example. The most common one that we're going to be using is the p-value method, but we can use either of the others to get the same result. So here's our example. We're going to test the effectiveness of a new teaching method for learning how to tell time. We're going to have two groups. One group uses the old method, so we'll call that group 1. So 13 out of 23, so 13 is going to be x1 out of 23, which is n1. Master the concept in one class period. A second group, we'll call that group 2, uses the new method. And 20 will be our x2 out of 27, which is n2. Master the concept in one class period. Is the new method more effective? And we give alpha of 0.05. Okay, so checking the requirements. Requirement 1 is simple random samples. It says random in the problem, so that's a good sign. Since there's students that are probably in his class and he's assigning them to two different techniques, it's maybe not a simple random sample, but it's not going to affect the results. Okay, so at least it's random and we can count that. Second requirement is that we have to be working with x out of n, and we are, so that one's check. And the second one, we need to check all of our n times p and n times q. So we don't have population proportions to plug in for p, we have to use the sample proportions. So let's first figure out what those are, and I'm going to do that down here because we need to summarize it for later anyway. P hat 1 is x1 divided by n1. And p hat 2 is x2 divided by n2. We get 0.741. So n1 is 23, p hat 1 is 0.565, and if you multiply those you get right around 13. I'm going to round these. N1 again is 23, Q1 is 1 minus P1, so it would be 0.435, and multiplying those you get right about 10. N2, there are 27 in that group, and the proportion is 0.741. That would give us right about 20, and N1, 27 times 1 minus P2, which would be 0.259, is about 7. So all of these numbers are greater than 5, and we can proceed. So we've checked all 3 requirements. So summarizing data, we have P1, X1, N1 here, P2, X2, N2. The only other thing we might want to do is do a pooled proportion. So we can take 13 plus 20 divided by 23 plus 27, and that should give you 0.66. And then the pooled Q is 1 minus that, which would be 0.34. So we should have all the numbers we need now to do the problem. Next step is to write our hypotheses. We're going to hypothesize that the 2 groups are the same, that there's no difference. And we can write that either way, either P1 equals P2 or the difference P1 minus P2 equals 0. The alternative hypothesis, we're wondering if the new method is more effective, and group 2 was getting the new method. So we would expect that group 2 is better, greater than group 1. And if you were to subtract those, if P1 was smaller than P2, or P2 is bigger than P1, if you subtract them you should get a negative number. So we'd say that the difference is less than 0. Okay. Either way you do that, it's a left-tailed test, which we'll need to know for later. So now let's look at the 3 ways to solve the problem. The first method we'll look at is the p-value method. Again, we're going to calculate a z-test statistic and use that to get a p-value which will compare to alpha. So the p-value, or the z-score, I'll just put the whole equation here. So now we can fill in the numbers. Our first sample proportion was 0.565. And we subtract the second sample proportion, 0.741. The difference between the population proportions from our hypothesis is 0. The pooled proportion was 0.66, and pooled Q would be 0.34. The first sample size is 23. Same thing over here on top, but our second sample size is 27. Again, do these equations in parts in your calculator and write down each part as you go. So when we calculate that all out, we should get z equals negative 1.31. Now, our alternative hypothesis, or let's put both hypotheses up here. P1 equals P2. Our alternative is that P1 would be not as effective as P2, so P2 should be bigger. So again, it's a left-tailed test. So we want the area to left of a z of negative 1.31. So negative 1.31 would be about right here. We're looking for this area as our p-value. So our normal CDF function, we can go from negative 99 to negative 1.31. The z distribution has a mean of 0 and a standard deviation of 1. And when you plug that in, you get 0.0951, which is our p-value. So we're going to compare the p-value to alpha. The alpha they gave us to use in the problem was 0.05, and our p-value is bigger than that. So our conclusion should be fail to reject the null hypothesis. And what does that mean in the context of the problem? If we fail to reject the null hypothesis, remember a null hypothesis with the two groups were the same. So we have to conclude that there's no difference between the two groups. Another way to write that is that the new method is not better than the old method. So doing this on the calculator, again, a two-proportion z-test. Make this go a little faster. In the stat menu, over to tests, and find two-proportion z-test. It's number 6. So our numbers are already in here. Our first sample had x equals 13 and n is 23. Second sample had x is 20 and n is 27. Okay, down here, our options, we wanted the new method, P2, to be better than the first method, so we used this sign. The P1 would be less than P2, and then we can go down and calculate. And here's our number. Z equals negative 1.31. The p-value is 0.0958. It gives you some other summary numbers as well. You can see it gives you the value of the sample proportion for each group. It gives you the pooled proportion, which was 0.66, and it recaps your sample sizes. So we're interested in z equals negative 1.31 and p-value is 0.0958. Okay, so the calculator z and our z ended up being exactly the same. Okay. And p-value 0.0958. A little bit different from what we got before, but basically the same number. Again, that's greater than alpha. Fail to reject the null hypothesis. Conclusion is the same. I am not going to keep writing that. Okay. So let's look at the other two methods, the critical value method and the confidence interval method. So critical value method, we need z alpha, and alpha is 0.05. And we can get that by looking up in the table. We have a one-tailed test. This is a left tail. And here's 0.05. So we go over to z, and we get 1.96. So that's our critical value for z. The z that we calculated up above was negative 1.31. And we're going to use the positive absolute value, because again we're just interested in how far away from the standard deviation, not necessarily the direction. So our test z is less than the critical z, which results in the conclusion fail to reject the null hypothesis. There's no difference between the two groups. And the last one, the confidence interval method. And let's just do that right in the calculator. So there is an equation for the margin of error that you could plug numbers into, but let's just look at how to do it on the calculator because that'll be the more common approach. So under the stat menu, over to tests, find the 2 proportion z interval. And there it is, it's letter B. Okay. The first sample had 13 out of 23. The second sample had 20 out of 27. The confidence level, we were given an alpha of 0.05 to work with, and the confidence level that corresponds to that is 0.95. They have to add up to 1, so 0.05 alpha and 0.95 confidence level. And then we can calculate, and there is our confidence interval. So negative 0.437 to positive 0.086. Let's just round them both to 3 digits. So that's our confidence interval. The way that we can interpret this, since we're looking at the differences between groups, if the difference is 0 and 0 is included in this confidence interval, since it goes from a negative number to a positive number, 0 is in here somewhere. If 0 is in it, that means it's possible that the difference between the 2 groups is 0. And that was our null hypothesis. So we have to fail to reject the null hypothesis because it's possible that the difference can be 0, since 0 is in the confidence interval. And again, you could write a conclusion that says that means that there's no difference between the 2 groups, or that group 2 isn't better than group 1. But the main idea is the same. For all 3 of these methods, we get the same result and same conclusion.